All right, let's begin. Welcome to, what is this? CS3510, L03A, and the topic of today is Quicksort. You guys have seen Quicksort before, right? In what class? 1332, yeah. It's a sorting algorithm. We don't really care about the fact that it sorts. We really care to use it as a model to define recursive, to talk intimately about recursive algorithms. Again, we're in the divide and conquer unit, right? So roughly, how does Quicksort work? It chooses a pivot, places it correctly, ensure things less than it are placed before it, ensure things greater than it are placed after it, recursively solve, sort above and below. Right. So what does this look like as a picture? You have some unsorted array, something like this. What you do is you're going to place a special element, the pivot, and then you're going to ensure everything below it, to the left of it, is less than it, and then everything above is greater than it. Then you're going to recursively sort the left and right half. And by doing so, you will sort the whole array, right? So if we were to talk about the algorithm for quicksort, it would look like this. And this should be mostly a review. Let's say we have an array and we have indices L and U. And what we're going to do is choose a pivot, and we're going to return the index from a partition function. Partition of A, L, and U. And then we're going to call quicksort on the left and right half, pi minus 1, and then quicksort on A, what is that, pi plus 1, comma u, and then we're going to just return A. There's also supposed to be a base case here. If L equals U, return A. Then we, of course, need an entrance call, which is going to be just the quicksort of A1, comma n for A having indices 1 to n. Some of you have asked, can I do 0 indexed or 1 indexed? It doesn't matter as long as you say which one you do, right? Sometimes it's easier to do 1 indexed. Sometimes you have habits and you want to do 0 indexing. Totally fine. Just as long as you specify which one you're doing. You say, let this be a 0 indexed array. Let's be a 1 indexed array. It's up to you. Right? This is quicksort. So first off, the recursive call is fine. We kind of get visually what that happens. But what does this partition function do? We need to talk about the partition function. We'll also have to talk about why it's called the partition function. But for now, any questions on the quicksort? The code of quicksort, right? It's coming back to you. It seems familiar, right? So what does partition do? Well, it partitions the array. And what does that do? We'll talk about that in a second. Partition takes on the array and these bounds, L and U, lower and upper. And what it's going to first do is choose a pivot element, P, to be the last element, A of U, let's say. Okay? And then it's going to keep 2 counters of L minus 1, and then for j in L to U minus 1, if A of j is less than or equal to the pivot, we're going to increment this I, and then we're going to swap A of I and A of j. And then at the end, we're going to swap A A of I plus 1 and A of U, and then we're going to return I plus 1, which will be the index of the pivot. So code, kind of not obvious what's going on here. But the best way to visualize it, let's just do an example, and we can see what I, J keep track of. It's called partition because it partitions the array into a few different places, right? So what those places are, we'll have to point out in the intermediary steps. It's going to be like before J, before I, between I and J, and then after J are going to be three distinct things. And then as it sort of like loops over, it's going to do something kind of nice for us, right? So let's suppose we have an array of the form 2, 8, 7, 1, 3, 5, 6, 4, okay? What we're going to do first is choose a partition item, a pivot, P here. And we'll put P as this 4. Now, there are several parts to Quicksort. There's choosing a pivot element, and then there's how do you recursively place sort the items, right? Quicksort is kind of cool in the sense, unlike the way we described merge sort at least, is that it's allowed to sort kind of in place, right? It doesn't need external memory. At least the way we presented merge sort is that we said it recursively copies the arrays over and stuff, but you could just do it in place to save. Here, as we've written it, it does it just in place. Things are swapped around in the memory. And the function is recursively called, but upon the indices L and U over and over, right? So what we're going to do is J is going to begin here, and then I is going to begin here, which is L minus 1, right? So what we're going to do first is we're going to enter the loop, and we're going to say if AJ is less than or equal to P, what is AJ here? It's going to be 2. We increment I. So now I and J are at the same index, and then we're going to swap. So we swap AI and AJ, but I and J are at the same index. So the first iteration of this one, at least, nothing happens. Then we increment the for loop, right? So after one execution step, we're going to look like this. I is going to be here, because I++, and then J is going to be here, and nothing has happened. Okay? P is still here, the pivot, right? Question so far on the execution. Okay. Is 8 less than 4? Okay. We're not going to plus I, and we're not going to swap anything. We're just going to increment the for loop. Okay. Is 7 less than 4? No. We're not going to increment I. We're not going to swap anything. We're just going to increment the for loop. Okay. Here we can illustrate kind of what is going on between the things. Okay. Anything before the index I, including the index I, is going to be things less than or equal to P, right? By incrementing, if you have an element that's less than P, you say I++ and you swap it around, right? So things before I are going to be less than or equal to P. If it's between I plus 1 and J, so it's in this kind of middle region here, what do you know about the elements that are between I plus 1 and J? Yeah. J skips over these if it's greater than it, right? So J is going to go farther away from I as long as things that are, those are greater than P, right? And what about after J plus 1? What are those items? Yeah, undetermined yet. This is why it's called partition, right? We have not even done a swap yet, though, but we're about to. We notice that J here, A of J is 1, which is less than or equal to 4. So we're going to increment I and then swap those around. So I is going to be incremented. Okay. J is here. We're going to swap I and J. So this is going to become 1, and this is going to become 8. Right? Notice how this kind of has like a flooding property. Small thing past j, push it to before I, wherever I happens to be. Right? So small thing is going to go that way, big thing is going to go that way. That's going to end up with our partition nice property. We want to end up like that picture where the big things are going to come after wherever the pivot is, and the small things are going to come before wherever the pivot is. Right? Is 8 less than or equal to j? Wait, we I plus plus, we said j was here, we swapped it, and now we're going to say we're at the next loop. So in fact, j gets incremented, right? Yes, okay. Question so far? Okay. Is 3 less than 4? Okay, so we're going to increment I. We're going to increment I. Then we're going to swap I and j here. So this is going to become 7. And this is going to become 3. Right? Then we increment j, because we're increasing the for loop, right? Notice how, again, in between I and j are things that are greater than j, but are waiting to be swapped out with something if it's the case that j happens to find anything after it that is swappable, right? So if j finds something here that's swappable, it's going to push it, it's going to swap with one of these things between I and j, right? So these eventually will move over here until j is exhausted out of the array. Is 5 greater than 4? If is 5 less than or equal to 4? No. So we say I plus plus. Excuse me, j plus plus. And then I is still here. Is 6 less than or equal to 4? The answer is no. So we say j plus plus. I'm just going to write it here. Now we're done. Notice that we've finished the for loop. Where does now where do we put the pivot? We chose the pivot in this specific case. It's not always true, but in this specific implementation of partition, the pivot is the last element. So now we need to go swap this with I plus 1, which happens to be right here. So what we're going to do then is erase this, put the 4 here, and then put the 8 here. Right? Then we're going to return I plus 1 as our pivot, which is going to be that thing. It's going to be, that's going to be our index, right? We're not going to return the element, but the index itself. So by the partition, this is how partition works, right? It has this very simple kind of like pushing and pulling going on, and it ends up with a very simple property where this last element is placed correctly where it's supposed to be. Things before the element are less than in it. Things after it are greater than it, but it's not sorted necessarily. It just has this very minimal property, right? Questions first off on the correctness of partition. Do we believe that it works? Okay. Second question, what's the runtime of partition? O of n, why?
Because there's n elements.
Yeah, there's one for loop. So what else is going on? Swapping, constant time. Yeah, I mean, that's obviously O of n, so let's just call it O of n. So the next question is, what does this make our runtime of Quicksort? Now, choosing a pivot is going to be basically the rest of the discussion of this part of the lecture. What happens? What kind of pivot can we choose? What is the runtime of T of n here, right? What is the worst possible thing it can do? What is the worst case pivot choice for Quicksort?
The smallest or biggest.
Yeah, it's the smallest or biggest. So in that case, we could say T of n is going to not split the array nicely or something like this. It's going to just choose the minimum element. And then one of the Quicksort recursive calls will be on one element, which will take constant time, and the other recursive call will be on n minus 1 elements, right? And then it takes how much additional work? Yeah, it's just the time of partition. So this is not a recurrence that we can apply the master theorem to, but what is this going to be? Yeah, why? Basically. You're going to unroll it. Like you could say, well, by evaluation t of n minus 1 is equal to t of n minus 2 plus O of n minus 1. So you could say that t of n is equal to t of n minus 2 plus O of n plus O of n minus 1, which is just O of n, right? So you say dot, 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 t of n is equal to t of 1 plus O of n plus O of n minus 1 plus, right? And then this happens to be n times, or at least O of n times, right? So that's like O of n squared, right? Now this is in the worst case, right? So if it chooses the pivot in a terrible sequence of decision making, if it has terrible decision making, and it gets extremely unlucky, then it runs in O of n squared steps, right? But one of the interesting things about, first of all, that's bad. What was the runtime of merge sort? Does anyone remember? It was n log n. N log n is much better than n squared. I mean, like n log n is basically linear time with a small catch. N squared is significantly worse than n log n time, right? So first of all, this is not very good. Merge sort beats this. But this worst case analysis kind of only happens when the pivot is chosen in a specific way, right? So most of the time that doesn't actually happen. So the average case of quicksort is actually pretty good. Before we talk about the average case, there's something called best case analysis, right? So let's suppose we are extremely lucky, and for some reason as we choose the things, that we always choose something like a median element to be our pivot, right? Suppose if we always chose the best thing. If we chose something that almost basically every time, suppose we got really lucky, and it partitioned the set exactly half each time, what would the runtime of our of quicksort be? Why? What's our recurrence? We always back up a step.
T of n over 2.
T of n over 2, yeah, because each one is divided in half. Yeah, 2 times that, because we have 2 recursive calls. Let's say each one is exactly nicely half, plus O of n. That is what? N log n, right? You guys should actually remember, you don't have to apply the master's theorem. You should recognize that's just the merge sort recurrence. In fact, it was even the FFT recurrence and some other things. It's like that's the one, right? So that you should know that one. That's, so in the best case, you get lucky, it's O of n, n log n, right? So like, what happens in practice? Like, when do you choose, is it going to be more like the worst case or more like the best case? And the answer is, suppose you choose a pivot, in perhaps not even in a strategy, but just by luck, that it is not a constant away from the min or max in this situation, but is closer to the min and max, but not in a bounded format. So suppose it's split, consider if we split the problem up in a very adversarial way, but at least definitely not constant. So what I'm going to do is analyze what happens if we split this up into a biased way, but not exactly a constantly biased way. So let T of n equal T of, let's say, 999 over 1,000 n plus 1 over 1,000, excuse me, T of 1 over 1,000 n plus O of n, right? And the point of quicksort today is going to be not really, I don't really care about quicksort. It's about like weird analysis of algorithms. So like, how would we compute the runtime of such a thing, right? Suppose we chose the elements in such a way so that it partitioned always some fraction, perhaps a small fraction, but a fraction nonetheless, and one that's a function of n and not a constant, right? How could we analyze such a recurrence? We can't just throw the master theorem at it in a black box way, but there's other things we can still do here.
Take the average.
We'll do that later, it turns out. But suppose in this specific case, So basically what we do is we're going to repeat the proof of the master theorem, essentially, right? So what we're going to have is a subproblem here of 999 over 1000n. And then this is going to be like 1 over 1000n. And then this is going to be something squared of that, and this is going to be something of that, and so on, right? At each level, how much work is done? Approximately n work is done at each level, right? Times the size of these subproblems. But what's the depth of such a tree, right? So this is going to divide out much faster than this. So in fact, these branches are going to be pretty short. So but we're looking for the max depth of the tree. It's not a nice tree. So let's look how deep this goes, right? When does this bottom out? According to the master theorem, it would be like, for what I does n over 1000 over 999 to the I equal O of 1. For what I is the depth here, repeatedly, you're going to repeatedly compute the subproblem of the subproblem and so on, and the problem is going to shrink pretty slowly, really, really small. This is like 1.001 something, really not fast at all, but it's going to shrink nonetheless, right? So if you were to do this, for what I is this going to work? This is a calculus one. Question? Okay. It's a log, by the way. I'll tell you guys, it's 1000 over 999. That's the base of n. What is that? Don't care. It's O of log n. Okay? Depth is log n. N work done at each level. Depth is log n. So we get that in this case, we get O of n log n. Right? N work done at each level. The depth is approximately log of n. A weird base log of n, but who cares? That's still log of n, as long as that's not like 1. I don't think you can have a log base 1. I think that's impossible. But this is not 1. It's something small, but it's definitely not 1. Either way, there's a change of base formula to log base 2. That's a constant, so this is just O of log n, right? You do n works each level, you get n log n, right? But notice what's really the difference between this one and this top one. It's just a slight difference. If you're promised that you pick the pivots, you don't always pick the pivots a constant away from the max or the min, but rather some growing function, perhaps very, very small, but some growing function away from the max or the min. That's enough for you to guarantee that the runtime will be n log n and not n squared. So what this really means is, that the average case runtime of Quicksort is pretty good. So what does average case runtime mean? Now, there is a whole theory of the average case analysis of algorithms. It's quite difficult. You could spend your life on this stuff. What is an average input? What does that really mean? The best way to think of it is like most of the time you'll never hit the worst case. So if you were to think about a picture, suppose you were plotting the time it takes, and you were plotting the inputs in some way, not just by size, but the actual inputs themselves, right? N squared would be like this, and then n log n would be kind of like that. It's slightly, that's too much. It's actually slightly better than linear, right? It's like that, right? So what it means is the runtime, if you were to somehow plot it, it would look like this. Right? For like 99.999% of the time, it's below this n log n function, but it's not always below n log n because there are some times you get unlucky. Very infrequently, in fact, I've put too many spikes here. Very infrequently will it exceed n log n, but it will still be below n squared. Yes?
For this one, isn't our best case also n log n?
Yes, but we don't know the best case. You don't always choose a pivot in the best case.
Yeah, so how would we get below n log n?
The runtime is bounded by, so it's not like below n log n. The definition of big O is that the runtime must be less than the function on all inputs. So it's technically correct here. But if you were to plot it, it would look kind of like that. It would look most of the time to be below log n. There are some inputs it would accidentally just be below n, right? It would be, who knows, right? But it would rarely exceed, it would exceed n log n, It would never exceed n squared. It would exceed n log n, but it would do so rarely. That's what average case is in some sense. So average case, it can be very, very difficult to do. But just intuitively, it's like most of the time in practice, like it works, right? For example, a hash function, there is no perfect hash function. By the pigeonhole principle, every hash function has a collision. We just don't know what they are. We don't know how to find them. But in theory, they exist. Now, experimentally, when you go and you run the hash function a bunch of times, you'll probably never find it. But it must exist. We just don't know how to find them. It's similar here. It's just like when you actually measure it with a stopwatch in some sense, it looks pretty good. So we want to prove next that Quicksort has, on the average, a n log n runtime on average, right? So there's two things you can do to choose the runtime to choose the pivot better, right? Basically, the whole thing is dependent upon the pivot. So what people will do here is, because you don't have any control over what the input is looking like. You can't guarantee, for example, that the input is a totally randomly sorted array. You have no control over that. You don't understand, to use big words here, what the distribution of what the inputs is coming from. What you do get to do is say something about the distribution of your own behavior. So what you do here is, in this line, instead of choosing the last element, you just choose a random element. Now, a random element, there's still a chance that you get unlucky, right? There's still a chance, there's a non-zero probability that every time you chose a random element, you happen to choose the minimum of the array. And then the second time you chose the second minimum, the second least element, and then the third least element, and the fourth least element. There is a probability that occurs. There's a very small probability that it occurs. It's the same way that if you flip a coin, there is a universe out there where you flip a coin 100 times and you get 100 heads in a row. That's not impossible. It's just very unlikely. So when you run Quicksort, most people implement Quicksort with a randomized thing simply to hit the average case in their control. Now, randomized Quicksort we need to now do the analysis of. And we're going to show that if you randomly choose the pivot with high probability, your runtime is going to be n log n. And basically it happens because average things happen on average. If you choose a random thing, it's probably not the min or max. It's probably close to the middle on average, right? That's kind of what's going to happen. And that's basically what we're going to certify in a second. But any questions on Quicksort before we get to the average case analysis? Right? Any questions on what we've said today so far? So what do we mean? What's the point of this average case analysis argument? It's like just to show you what a complex analysis of the running time of an algorithm could be. We'll do this analysis. It's sort of the point of today. Sometimes analyzing such recurrences is itself like a dark art. It's one of those things that it's like, how do I say this? Like, there are some fields of math that are very structured and nice, and everyone knows how they work. There are some fields that are just kind of like magic, and you don't know how the people in this field do any work, but somehow like it's all heuristics, and you just kind of go along with it. We'll do a recurrence like that today just to show you what it looks like. Other fields like that are like cryptanalysis, differential equations. Sometimes you're just throwing stuff together and then you end up with the right answer somehow, and it's not obvious how that works. But that's basically what we're going to prove today in just a second, right? Questions so far? Okay, so right. Suppose we randomly choose an element, right? T of n is going to the runtime is going to be partitioned. Let's say A has size 1 to n, and we randomly choose an element to pivot upon, right? If we randomly choose an element to pivot upon, let's say it's element I. We're going to break up the array into two parts, and then we're going to recursively solve each of those, right? So what we're going to do is this is going to be t of, let's say, some I plus t of, I think it's n minus I plus, let's say, n, right? So let's suppose we chose element I. we split it up into two parts like this. Fine. What we want to do is now, if we chose I uniformly random with equal probability to be any of the elements in there, what we can do then is have our recurrence simply average over all possible I, right? So no matter, this could be 1 and n minus 1, this could be 2 and n minus 2, this could be 3 and n minus 3, this could be n over 2 and n over 2, this could be n over 3 and 2n over 3, and so on, right? However that I is going to work, we can average over all possible choices of I if we choose I uniformly random. So what we'll do is choose I uniformly random. T of n is equal to 1 over n, the sum of I equals 0 to n minus 1 of t of I, plus t of n minus I, plus n. Now that's really the recurrence we're going to be solving today. Obviously there's no master theorem involved. We can't just say A, B, and D. It's kind of complicated. So this is the dark art part, so to speak, right? What's the first argument we can make about such a recurrence? There should be something that jumps out to you about this, aesthetically. What's really the difference between t of I and t of n minus I? They're really, so when you add them up, they're really the same thing in a different order. 1 plus 2 plus 3 plus 4 is in an increasing order, and this is going to be 4 plus 3 plus 2 plus 1 in the opposite order, right? So if you have t1, t2, all the way to tn minus 1, that's actually the same thing in an opposite order of t of n minus 1, t of n minus 2, t of 1, right? Those are the, if you add up the top, it's the same as adding up the bottom, but it's just in the opposite order. So what we could do is distribute the sum and then write this one backwards. This is going to be t of 1 plus t of 2 plus t of 3. This is going to be the same thing, but in the opposite order. So in fact, this is going to be equal to t of n is equal to 1 over n times what? Yeah, 2 times what? Yes, but to be simpler, we'll put t of I. Yeah. Okay. First argument by symmetry, one of those dark art things. How would you come out of this? Rabbit out of the hat kind of thing. We've simplified the recurrence a little bit, right? Now here's the part where, how do we simplify that? We got a sum here. I don't like that. I would like to prefer to have a couple constant amount of terms. Here's what we're going to do. We're going to sort of telescope the sum away, okay? First, we're going to evaluate at, we're going to go from n to n minus 1. So when we evaluate at n minus 1, we're going to have t of n is equal to, wait, am I doing this right? My mistake. I'm going to first multiply through by n, right? So this is going to be n times t of n, which is equal to 2 times the sum of I equals 0 to n minus 1 of t of I plus n squared, right? Then I'm going to evaluate at, from n to n minus 1, we're going to get n minus 1 t of n minus 1, which is equal to 2 times the sum of I equals 0 to n minus 2 here of t of I, plus n minus 1 squared, right? So this is the sum we're trying to solve for. We've evaluated it from n to n minus 1 to get this thing here, right? Importantly is that the sums are almost the same. So suppose we took the difference of those two equations. What would we get? If we took the difference of those two, we would get n t of n minus n minus 1 t of n minus 1 is equal to what? Most of the terms of the sum are the same except what? Yeah, the n minus 1th term of the sum. This whole thing is going to basically cancel out all of that except one thing. So what do I write here? Yeah. 2 times t of n minus 1. And then what's left? What is n squared minus n minus 1 squared? Close. Almost, basically. Yeah, it's going to be 2n something, right? What is it? Yeah. Okay. Okay, well, I have a tn minus 1 over here. I have a tn minus 1 over here. We can get a recurrence. N, t of n, is equal to what times t of n minus 1? What goes here? We have n minus 1, negative n minus 1s. We have negative n minus 1, t of n minus 1s over here. And we have 2 t of n minus 1s over there. If we move that to the other side, how many t of n minus 1s do I have? Yes. And then I'm just going to ignore the 1 because I don't like it. It's going to make things worse. Another dark art trick. 2n. Okay. Okay, let's divide by n times n plus 1. We're going to have over here t of n over n plus 1 is going to be equal to, there's going to be t of n minus 1 over n plus 2 over n plus 1. Is that correct? Okay. Now, why do we care about this? Why do we do this? That's an n and an n plus 1. That's an n minus 1 and an n. So really, this is just an advancement of this, if you think about it, right? So what we can do is, it's the same way we did the t of n minus 1, t of n is t of n minus 1 plus O of n. We can, quote unquote, kind of unroll this, right, in the same way. So if we were to evaluate this, we get that t of n minus 1 over n plus 1 minus 1 is n. We get t of n minus 2 over here. And then we have n minus 1 over here. And then we get 2 over n here. Do we agree? All I've taken is taking that and evaluate at n. Instead of n, we evaluate n plus n minus 1, right? But we can now just take this and then plug it in here, right? So we're going to get t of n over n plus 1 is equal to that thing, which is t of n minus 2 over n minus 1 plus 2 over n plus 2 over n plus 1. Right? Now, suppose I did it another time, a second time. I go from t of n minus 2 to t of n minus 3. What are we going to get? We're going to get t of n over n plus 1 is equal to t of n minus 3 over n minus 2 plus 2 over n minus 1 plus 2 over n minus n plus 1, right? Wait. Plus 2 over n plus 2 over n plus 1. Right? Do we agree? So every time I decrease the n's in this term by 1, I add a term here. It's like it's like a factory. It's adding a bunch of terms out there, right? So let's bottom out. T of n over n plus 1 is equal to what? T of 1 over 2 plus, so that's going to bottom out. And what's our sum going to be? Let's call it 2 times what? The sum is going to be from what to what? Let's say I equals, what's our lower bound? It's actually not particularly important. Well, it won't be 0, it turns out. We'll have a little bit of base case stuff going on.
1.
Not quite 1. Not 2. 3. I have 3 here. Why? So, and then what's the top is going to be, again, not particularly important. This is going to be n plus 1. And then what goes here?
2.
No, not 1. 1 over what? 1 over I. Okay. So we have some constant plus the sum. Okay. Does anyone recognize that sum? There's a name for it. Does anyone know the name of that sum? Again, I don't expect you to know that, but if you, it's the harmonic numbers. Now, okay, so does anyone know what the nth harmonic number is? H of n is equal to the sum of, I think, I equals 1 to n of 1 over I, right? That's the definition of the harmonic numbers. You may recall something about this from a little bit of calculus. What are the, does anyone know the properties of, any property about the harmonic numbers?
Or divergent.
Yeah, it diverges. So definitely it's not a constant, first off, right? It does diverge. Now when it's squared, it does converge, right? But it diverges, certainly. Does anyone know the closed form of this? You shouldn't. You can prove, and we do this in 2050 sometimes, you can prove that basically it's kind of asymptotically about log n. But the exact formulation is kind of like, okay, it's ln of n, and again, this is not important at all, plus the Euler-Macaroni constant plus 1 over 2n minus the sum of Bernoulli numbers, b2k over 2kn to the 2k. Now, don't really care, any of that. What important is that h of n is what? Yeah. Constant, that's small if n is big. That's making it smaller. So whatever, just ignore all that. We get log of n. That's actually pretty easy to prove with induction as well. That they are increasing. They're not constant, but not only are they not constant, but this is their upper bound, right? Some constant times log of n. It's like less than 2 as well, the constant, I think. So anyway, that's all we really need. Because then when we have t of n over n plus 1 is equal to t of 1 over 2 plus 2 times the sum of I equals 3 to n plus 1 of 1 over I, we can say that this sum here is approximately just the nth harmonic number. The terms that are missing are basically going to be our constant stuff because we still have a sum of n terms. So it's still approximately the nth harmonic number up to a couple constants, right? Log of n minus 1 is still log of n and so on. So what is this going to be? This is going to be t of n over n plus 1 is equal to t of 1 over 2 plus 2 times O of log n, right? This constant, that's a constant. T of n plus 1 is a constant. So t of n over n is equal to O of log n. Plus a constant. Multiply by a constant, add a constant, O of log n. Last thing, multiply both sides by n. All right, done. QED. That's the analysis to show if we average over all possible elements, our expected running time is going to be n log n. Questions on that? Again, analysis, now that we've seen the analysis, that's kind of why I'm interested in Quicksort rather than like an actual algorithm to sort. I'm interested in this kind of argument. Yes?
Why did we start with the ti and the tn minus I terms plus n, and not like O of n or something?
Simply because when you do O of n, so n squared and n minus 1 squared are both O of n squared. But the subtraction of those will not be a constant. It'll be a linear term.
Okay.
So lots of little black magic details, which is why I kind of like prefaced with that.
So by writing it as n, or like any constant times n, instead of writing it O of n squared, instead of getting O of n squared minus O of n squared, which is just O of n squared, you get a specific thing that turns linear?
Yes,
Got it.
exactly, exactly. And it would have been more proper of me to write, but I didn't do it for simplicity. Instead of plus n steps, it's some constant times n. Yes. So C of n, and then when you work out the math, you still get a constant. Everything washes away quite nicely, right? Any more retrospective comments on the analysis now that we've finished it? Now, again, it's not totally expected that you would come up with this on your own, like with no help or anything like this. I mean, it is expected you understood the argument, but like in a vacuum, you shouldn't be able to come up with this by yourself. Yes?
Could you briefly explain just how we went from like t of n plus 1 to t of n over n again?
Here?
Yes.
Oh, I can ignore constants. I can do whatever I want. So just like, obviously that's like, oh, well, fine. Well, I mean, I could, something like this, right? Working without big O, you have to take care of certain things. When you're working in the asymptotic regime, you can relax stuff and just say, I'm going to ignore that. I don't need it. It goes away. Kind of fair, right? Dividing by, we're trying to just find the asymptotics of t of n and not some precise exact formula. And you may solve such recurrences, not like this, but in combo where you need to know the constants and stuff. You would have to keep track of that, obviously. But I don't have to, so it's fine. More questions? Yes?
Why did you start from I equals 3?
Because the sum, now the bad answer is that it doesn't really matter because it's still O of n summation. O of n minus 3 things is going to be still O of n. But the sum stops right before it does here. We want this to be not negative so far, and I think 3 was the one that makes this not negative, right? Yes. More questions? All right, when we come back from the break, we'll talk about quick select.